Good day, everyone. Recap of what is DFM. In our last video, we covered Design for Manufacturing, DFM, a strategy that optimizes your design for efficient and cost-effective production by focusing on material choice, component placement, and footprint accuracy early on. DFM reduces errors and simplifies the manufacturing process. Now let's move forward and understand another critical design strategy, DFA. What is DFA? DFA stands for Design for Assembly. It's a design approach aimed at minimizing product costs by simplifying the assembly process. DFA focuses on 4 key factors: reducing parts count, assembly time, part costs, and optimizing the assembly process. Let's now see how DFA is specifically applied in PCB design. DFA and PCB design. In PCB design, DFA optimizes the design for efficient assembly, reducing the number of parts and simplifying the placement and connection of components. Next, let's understand how DFA and DFM work together during PCB manufacturing. Role of DFA and DFM in PCB manufacturing. DFM, Design for Manufacturability, optimizes design for efficient manufacturing, reducing waste and ensuring compatibility with fabrication methods. DFA, Design for Assembly, simplifies component placement, reduces handling, and minimizes errors, speeding up and lowering assembly costs. Together, DFM and DFA streamline the PCB production process, ensuring both efficient manufacturing and fast, cost-effective assembly. Now, let's dive deeper into DFA and its intent in the design phase. DFA, Design Intent. DFA helps reduce component procurement and placement costs, key expenses in PCB assembly. It prevents rework and redesign by addressing assembly issues early in the design phase. The 2 primary stages in PCB assembly, they are PCB prototype assembly and PCB production assembly. PCB prototype assembly. In prototype assembly, accuracy is critical. Components are verified for correctness and secure placement. Clearances and tolerances are carefully maintained to prevent issues in later stages. PCB production assembly. For production assembly, efficiency is key. Large-scale production is optimized for cost savings. Testability and reliability are prioritized, ensuring high performance and long-term durability. With the basics covered, let's move on to the essential considerations for designing a PCB ready for assembly. Essential considerations for designing a PCB for assembly. To design a PCB ready for assembly, several key practices must be followed. Use correct file formats like Gerber, BOM, and ODB++ to ensure smooth communication with manufacturers. Follow silkscreen guidelines like proper font size, line width, and clearance from pads. Maintain optimal spacing for soldering and signal integrity. Ensure enough spacing between parts, edges, and sensitive components like BGAs. Choose components that are readily available to prevent delays in production. While following these practices, it's also important to recognize common DFA issues and how to resolve them. Common DFA issues and resolutions. Let's explore common design for assembly DFA issues and their effective resolutions. Footprint mismatch occurs when components listed in the BOM don't align with the CAD footprints. Resolution: verify that BOM components match the correct CAD footprints for proper assembly. Incorrect or unclear component orientation can lead to assembly errors. Resolution: update silkscreen and assembly drawings to ensure accurate orientation. Components positioned too closely can hinder assembly. Resolution: maintain proper spacing to facilitate easier assembly. Mismatches between part numbers and descriptions can cause procurement and assembly errors. Resolution: review and update BOM entries to ensure consistency. Understanding and addressing these issues can greatly reduce costs. Let's now explore the key factors that impact PCB assembly costs. Factors impacting PCB assembly costs. Several factors impact the costs of PCB assembly, including turnaround time, technology used, component packages, and the complexity of the PCB. DFA helps reduce costs by optimizing these factors for cost-effective assembly. Finally, let's summarize everything we've learned about DFA. Conclusion: by focusing on simplicity and efficiency, DFA reduces costs, minimizes assembly time, and ensures high-quality production. With the right design choices, DFA optimizes the assembly process for faster turnaround and reduced production costs. Next video, DFT. In the upcoming video, we'll explore design for testing, DFT, focusing on strategies to enhance your PCB's testability, ensuring efficient and accurate testing processes for higher reliability and reduced production costs. Thank you for watching and stay tuned for more in our Back to Basics series.